Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. The previous episode claim was awesome. We have now a pretty code and it becomes much easier to debug and optimize it. I was hoping to make this episode about double prime optimization, just like we did in episode 11 with big primes. Let's quickly jump to that. So far we have been searching for smooth value b. Now let's make the condition more loose and also include the value qb, where q is a small prime number outside the prime base. So the condition is even looser. Instead of having q to be a prime, it can be a coprime of two small primes outside the prime base. So this is what I was hoping to do with the double prime optimization. But taking two primes instead of one, it creates few challenges. How we are separating two and one primes? Once we understand that those are two primes, how do we factor it? What will be the most efficient method for it? Once we obtain a new relation that has two big primes with all other primes in our prime base, how do we eliminate it? I was trying to solve 3 by including the two big primes in the prime base, just for the matrix calculation, since it's already having an elimination logic. But when I did that, the memory exploded. It was bad. The matrix worked amazingly fast, it easily digesting 200 case variables, but then it ran out of juice, and everything becomes super slow, until some time later it crashed on out of memory. So I turned to the heavy debug tools. I started to profile the memory, examine the thread, and consider new code strategies. I ended up with a bunch of small optimizations that nearly cut the memory usage by 300%. But still, I couldn't feed the matrix monster. LOL. So now I will show you all the small optimizations that I came out with, especially the -1 prime. Well, this one is actually a bug. Um, I hope that in the future episode I will be able to find a solution for double prime optimization. Okay, so in this episode we are talking about memory optimizations and the -1 bug improvement. It turns out that 2/3 of the time we are working on negative numbers. During the sieve we are trying to compute a log of a negative number. It returns a none, not a number. That fails all of our estimations. So by fixing it and adding -1 to our prime base, we gain about 300% speed up for our sieving. We invest 400 megabytes into the wheels. After throwing them into the dynamic cache, the memory usage dropped to just 10 megabytes or even lower. But it's not as big as what we spend on big integers. Those use interarrays behind the scenes and can easily grow into a couple of gigabytes. By replacing mod and divide with divide and reminder method, it cuts the big integer memory usage by half. The biggest memory monster is the matrix. You can barely spot it while not using the double prime optimization, but I figure that we should not eliminate eliminators. We're actually already not doing that, but there is another optimization that takes it a little bit further. It's both a big memory and a performance gain. Well, not a big, but a gain. And after all of those optimizations, the bottleneck moved from Siever to the vector extractor, which was super cool to see. So let me now show you all of those things in the source code, and also I'll show you how much time we are, how much speed up we are talking about. All right. Okay. So now instead of two sievers, we have two vector extractors. I told you in the last episode that we need to add special logic to allow them to be multi-threaded. I'm going to show you how I did it. But before that, let's talk about the 300% speed up for sieving optimization. In the siever, we had mass log of a negative value that returned not a number result. And it made base log not a number result. And it failed this if condition. So none of the smooth files we found were actually submitted. By turning it into a positive value, it solves this bug and it makes the entire process 300% faster. Awesome. The next part of that optimization is happening in vector extractor. So in here, when we are doing the extract vector, and if the value is smaller than 0, then we are setting the first value to be set for the -1. And let me show you that in the prime base. So the prime base adds -1 at the very beginning, even before entering the loop during the construction of the prime base. And here I'm starting from 1 instead of 0. Yeah, that's it. The rest didn't change. Now, how did I made it support multi-threading? So the big primes, when calling it big prime, yeah, just that. Added synchronized. And let me explain you why it's safe. Because we have most of the work done on the actual vector extraction, that big prime happening very fast. So it can create bugs if two threads will run into this simultaneously, but since it's happening pretty fast, there is no big deal of synchronizing it. And so there is no performance loss in here. Yeah, so this is this part. Now let's talk about the wheels optimization. In wheels, which is polyminor, that calls to build wheels, it's been creating new object here all the time. So I created a wheel pool that when calling to get method, it will either take an available wheel from the wheels queue, which is concurrent link queue to support multi-threading. And once who is using it is done with it, it will call to put to return it back. And that is called by Sieve. Once it's done running and extracting the values, it will run on the polynomial data and return all the wheels. Cool. That drops from 400 megabytes to 10 megabytes and even less. The next optimization is the big integer. So back to vector extractor, extract vector. During the vector extraction, we used to call to value mod p. And if that result was 0, then we would do value divide by p. Those two creates two big integer values. And here it's done more optimally. So the result is containing both the mode and the division value. And it takes half of the space. So that's a big save. And then finally, the monster, which is actually not such a monster when running on just relatively small number of vectors. Let me show you the matrix. So in here, we used to call to, can I show you the diff? No. We used to have a method for adding an item to eliminators map, or calling to extract solution. But what I did now is, after the first eliminator index or failed to be eliminated, then we should not continue and eliminate other indexes of this eliminator. We can simply put it into the map and be done with it. It saves on space, it saves on performance. It's not a huge improvement. It doesn't change the big O nation, but it saves on memory. So that was cool. Now let me show you some of the executions. Let's see what I got configured now. Let's make it 220. So I've been working with a J profiler. With J profile, it has this cool thread image. So for all of the threads, I added a name. This one is polyminer. This one is Sieve, and so on. Now we can see what is the usage of each thread. Green means it's running. Yellow means it's waiting. So the Sieve runs all the time. Then the vector extractors runs half of the time, and the polyminer only works a little bit. So that allowed me to see that the bottleneck is not in the Sieve, but with vector extraction. I wanted to be not fully green. Well, it helped me to realize how to optimize it. Also, check out the live memory. That's a pretty cool window as well. It shows that most of the memory is taken by the mutable big integer. It's part of the big integer, and the int array also part of them. All three of those are used by big integer. Next long, this is used by the metrics. The vectors are saved in longs. Big integer again. And wheels only take 10 megabytes instead of 400 as it was before. Yeah, and let me show you the execution. What is the result of it? So I made two executions for 200 bits. Now it runs under 40 seconds, which is pretty amazing. It's almost 2 times faster than the last time we've been running it, just thanks to the -1 optimization. Yeah, and also the memory save, which also speed things up. The matrix only takes 1.3 seconds to execute during the entire things, which is almost 10K vectors. Also run 220 bits. It takes long time, relatively long, a little bit less than 5 minutes. In here, the matrix took almost 8 seconds. So it's exponential in time, but it's not that bad. And yeah, this is the new numbers that we can tackle. Memory definitely becomes a thing now that we should consider going after the bigger numbers. And so we will continue doing. Please let me know if you have any questions in the Facebook group or comment below. And I'm going to publish the source code together with this document in GitHub. See you next time. Bye.